Welcome to Chapter 7, Ionic Equilibria. Now we are going to relate the strength of a weak acid and a weak base to the respective dissociation constant Ka and Kb. For strong acid, it is completely dissociated in aqueous solution. So when we want to calculate the pH, we use negative log H+. For weak acid, it is partially dissociated in aqueous solution. Therefore, we use reversible arrow. If we want to calculate the pH, we use concentration of hydronium ion. Now, let's go back to weak acid. Acid react with base, produce conjugate base and conjugate acid. Okay, so at equilibrium, an aqueous solution of weak acid contains a mixture of non-ionized acid, that is Ha, and its conjugate base. Okay, if we look at acid dissociation constant, if we relate back to equilibrium constant in chapter 6, chemical equilibrium, it is the expression of product over reactant. Okay, so this is the product. Another one is the reactant. But we do not add in water into the expression in the reactant because the concentration of liquid or water is constant. And also from chapter 6, we have learned about degree of dissociation. For weak acid, we will calculate how much acid dissociate over the initial concentration of weak acid. Now, what does the magnitude of Ka indicates? It indicates the tendency of acid to ionize in water, meaning that the larger the value of Ka, the stronger the acid. Okay, why do we say this? If we want to know if an acid strong or not, if we have higher concentration of hydronium ion, means it will be strong acid. So if let's say we have more or higher concentration of hydronium ion, mathematically Ka will increase. So if concentration of hydronium ion increase, Ka increase, it is a stronger acid. So the same goes for if hydronium ion concentration decrease, then Ka will decrease. So if we have less concentration than of hydronium ion, Ka decrease, it shows that it is a weaker acid. Okay, for most weak acid, the Ka values range from 10 to the power of negative 2 to 10 to the power of negative 10. If the Ka value you calculated is more than 1, means that it is a strong acid because it will completely ionize. Okay, now let's look at the third one because the first one and second one we have learned just now. So the percentage ionization of a weak acid decreases as the molarity of the solution increases. Now, the same goes for weak base if we want to look at Kb. Okay, so in your notes, please make correction. It should be Kb. Okay, B stands for base. Now, same thing again. The expression for Kb is product over reactant. And then we do not include water into the expression because the concentration of water is constant. So for base, we will have hydroxide ion. Same thing, we can calculate the degree of dissociation of weak base. We also can calculate the degree of dissociation for weak base. That is how much weak base dissociate over the initial concentration of weak base. Okay, now let's look at what does the magnitude means for Kb. Okay, if let's say Kb is larger, means that it is a stronger base. Okay, so if we want to know whether it's strong base or not, we look at the concentration of OH minus. If hydroxide ion concentration is higher, means it will be a strong base. Okay, so if we look at this, if the concentration of hydroxide ion increase, Kb will also increase. Okay, so it is a stronger base. Okay, the other way around, if the hydroxide ion concentration decrease, Kb will also decrease. So it is a weaker base. Okay, so for most of the weak base, the value range from 10 to the power of negative 2, okay, to 10 to the power of negative 10. Okay, so this is Kb. So if Kb is larger than 1, meaning that it completely ionized and it is a strong base. So these are the examples of weak acid and weak base. Now, what is the relationship between Ka and Kb? Okay, now we can consider the acid-base conjugate pair of ammonium ion and ammonia. Okay, when they dissociate in water, you will get these two reversible reactions. So here, ammonium is as acid, ammonia is base. So for ammonium ion, we get Ka. For ammonia is base, we get Kb. When you multiply Ka and Kb, and then when you cancel off, you will get H3O plus concentration multiplied by OH minus. And if you can remember ionic product is Kw equals to concentration of hydronium ion times hydroxide ion. And the value is constant. That is 1 times 10 to the power of negative 14. Okay, so this is the table to show the relationship between Ka and Kb. Okay, let's look at this hydrogen fluoride. It's a weak acid. Okay, so if we know the Ka, we can find the Kb as well, because Ka times Kb equals to Kw. So if we look at this, 6.8 times 10 to the power of negative 4 times 1.5 times 10 to the power of negative 11, we will get 1.0 times 10 to the power of negative 14. Okay, so that's all for this part, Ka and Kb. Remember, you can relate back to chemical equilibrium on how to write the expression for Ka and Kb. Okay, that's all. And then remember, the higher the Ka or the higher the Kb means that it's a strong acid or strong base. Okay, that's all for this lesson.